Welcome back. In the last part of this lecture, we're going to be talking about sums of terms of arithmetic sequences and sums of terms of geometric sequences. If we have an arithmetic sequence, then to find the sum of the first n terms, the notation we're using there is Sn, sum of the first n terms. All we need to know is the first term, the last term, and how many terms we have. It's number of terms divided by 2, multiplied by first term plus last term added together. So if we're looking at this first problem, we have a sequence given to us, and you can confirm in the same way that we did back in 13.2 that this is an arithmetic sequence. And we're looking at finding, here it says the first 50 terms, find the sum of them. So we know how many terms there are. There's 50 terms. We know what the first term is. We can find that out with just a little bit of work here. We're looking at 3 times 1 plus 2, which is 5. And we have the 50th term in our sequence. That's 3 times 50 plus 2, which is 152. So then the sum of the first 50 terms, which is the sum from k being 1 to 50 of 3k plus 2, should be number of terms divided by 2 multiplied by last term plus first term. And I just have to calculate that out, and that's 3,925. This one's a little bit more complicated because we don't have the formula for the sequence given to us, and we also don't know how many terms we have in the sequence. One thing that we know is that the first term for sure is 100 and the last term is 223. We can also see that it's an arithmetic sequence pretty easily because each time you are indeed going up by adding 3. So if we wanted to, we could figure out what is the formula for this sequence. And in fact, we're going to have to do that because we need to know how many terms there are in the sequence, which means we need to find out 223 is which term in the sequence. A what? What is it? Is it the 10th term, the 50th term? What is it? So we're going to start off by saying we know that the first term is 100, and we know that the common difference is 3. So the formula for an is that it's 100, the first term, plus n minus 1 times that difference, which if you were to clean that up, you would get 3n plus 97. So once you know that, you can say, well, good, which term then is 223? Well, 223 would be 3n plus 97 for some n, and then we just need to solve for what n is. And I find that n is 42. So that means that A42 is 223, that it's the 42nd term in the sequence. So now if you're looking at all those numbers from 100 and 103 and 106 all the way up to 223, that's the sum of the first 42 terms in the sequence, and the formula for that is number of terms divided by 2 times last term plus first term, which is 6,783. Now, if it's a geometric sequence, then we have a formula for that as well. And for that, we just need to know the first term, we need to know the common ratio r, and we need to know how many terms n that we have in the sequence that we're looking to sum up. So if we're looking at this, we want the first 10 terms of this sequence, and this is maybe not as obvious as to whether it's geometric or arithmetic. So again, this is where you use your calculator to find out. If you were to look at 2/9 minus 1/27, 4/3 minus 2/9, those are not the same. You'd get two different differences, which means this is not arithmetic. If, on the other hand, you looked at division, 2/9 divided by 1/27, 4/3 divided by 2/9, 8 divided by 4/3, all of those are the same. Those are all equal to 6. Our common ratio is 6. So here we know our first term is 1/27th, and our common ratio is 6. So that means that if we're looking for the first 10 terms to be added up, well, that would be my first term multiplied by 1 minus r to the n over 1 minus r. And then just a little bit of cleaning things up, and then that'll be that. So 1 minus 6 to the 10 1 minus 6, and the negatives cancel each other out, and actually the 5 on the bottom goes into the top nicely, and so you are going to get as your answer 12,093,235 all over 27, and that's the sum of the first 10 terms of your sequence. Now, if we have an infinite sum, so here this is not a finite sum from 1 up to whatever. Here we have an infinite sum of all of the terms in the sequence. So the sum of terms in a sequence where the sequence goes on forever. So here we have a little side condition as to when this sum will actually be a finite number. If your common ratio r, if the absolute value of that is less than 1, then you will have a finite sum for that infinite sequence, that if you add up all those infinitely many terms together, it will add up to a nice finite number. However, if r is 1 or larger, or -1 and smaller, then you won't get a finite number for your sum. So when we're looking at something like the first one, the first thing I noticed that this is, again, geometric. We're not going up by adding the same amount each time. We're going up by multiplying each time, in this case by 2/3. That's our common ratio. So 2/3, 2/3, 2/3, and so on. Our value for r is 2/3, and that is definitely something where the absolute value of it is less than 1. So if you were to look at taking all of these things, 2 plus 4/3 plus 8/9 plus 16/27, and so on, and you wanted to add up all infinitely many of those terms, since r has an absolute value that's less than 1, we will have a sum, and that sum will be our first term, which is a times 1 over 1 minus r. And if you were to just clean things up there, that denominator, that 1 minus 2/3, that's a third, so you'd have 2 times 1 over 1/3, which simplifies to give you 6. So even though you have infinitely many things all being added together, all infinitely many of them adds up to a nice finite number, and that number happens to be 6. The second one, it's less obvious maybe that this is something that's a geometric sequence where we're adding up infinitely many terms. If you're thinking about this, if you're thinking about ak being 3 to the k over 2 to the k minus 1, you can say, well then, ak minus 1, the previous term, would be 1 power less on the top and 1 power less on the bottom. And if you were to look at ak divided by ak minus 1, that would be 3 to the k over 2 to the k minus 1 divided by 3 to the k minus 1 over 2 to the k minus 2, or 3 to the k over 2 to the k minus 1 times 2 to the k minus 2 over 3 to the k minus 1. If you were to clean this up, the 3's will cancel nicely, leaving you a 3 in the numerator, and the 2's to powers will cancel, leaving you a 2 in the denominator. So you can see this is geometric. It's geometric because we do have a common ratio, but that common ratio is 3/2. Each time we're going up by multiplying by 3/2. And so for this, I would say for this problem, there is no sum. So this sum is not finite, and that's because the size of r is definitely more than 1. In fact, if the size of r, absolute value of it, is 1 or larger, then the sum of a geometric series will not converge. It will not be a finite number. So what is the sum of all that? The answer is there is no sum. It's going to become infinitely large. Last one here, we can confirm pretty quickly that this is geometric. Again, AK would be 1 over 2 to the k minus 1, and AK minus 1 would be 1 power less. And if you looked at the ratio of AK over AK minus 1, you would get one half. So our ratio here, our ratio is 1/2. Each time we're going up by multiplying by 1/2. And so this is something where, yes, we will have a sum. The first term, a1, should be 1 over 2 to the 1 minus 1. That's 1 over 2 to the 0, which is 1. So our first term is 1, and our common ratio is 1/2. So in other words, this sum that we're looking at, it's the sum of 1 plus a half plus a quarter plus an eighth plus a 16th. So each time the numbers go up by multiplying by a half. And we definitely know that since r has an absolute value that's less than 1, that this sum will be a finite number. And we can find that sum by taking our first term times 1 over 1 minus r. So that's 1 times 1 over 1/2, which is 2. So 1 plus a half plus a quarter plus an eighth plus a 16th plus and so on, all those infinitely many terms will all add up to 2.